Hello everyone, we were going through seismic design of steel buildings. In the last class, we have discussed various codal guidelines from IS 18168 related to seismic design and ductile detailing of structural bracage and shear links. While the structural bracage form the most ductile element in case of concentrically braced frames, shear links are the most ductile element in the eccentrically braced frame. Today, we will illustrate the design of a structural brace using an example problem related to a special concentrically braced frame. So, in this example problem, we are told to design a residential building with shown plan and elevation details, and the building is to be constructed at a medium soil site located in seismic zone 5. The lateral load resisting system comprises of a steel special concentrically braced frame. The dimensions, loadings and material properties are listed further. We will go through them and we will try to obtain a suitable section for the structural brace for good seismic resistance. So, we are utilizing the same frame which we have designed it using moment resisting frame, that is, we have designed a special moment resisting frame or SMRF. For the same frame, what we are now doing is that we are implementing structural bracage in the frame, which means all these diagonal members are our structural brace. These diagonal members are connected using pins or using simple supports at these joints. Similarly, in the other way as well. Further, as we have mentioned it earlier, that these structural braces are to be provided throughout the height of the building as shown in this case. Now, at this point, the column and beam dimensions remain the same. We will come to the section which we have used for structural brace. The loading and material properties are similar to that of the moment resisting frame building. It is intuitive to say that this building comprising of special concentrically braced frame is more stiff as compared to the SMRF building, that is the special moment resisting frame building. With the increased stiffness, we also expect that the lateral drift in this building will be reduced. That is the whole rationale behind provision of braced frames in our structural systems. Now, we have obtained a numerical model on StatPro as shown over here, and we have presented here the utilization ratio of various members. As we can see that the utilization ratio is very well less than 1, and it is the highest value for either bracage or beams. Of course, if your beams are failing before a structural bracage, that is not a desirable situation. In case of our special concentrically braced frame, we want our failure to initiate in these structural bracage. Now, at this point, I would also like to reiterate that here we have used diagonal bracing. We could have used an X bracing as well. We could also have used inverted V or V bracing as well. K bracing is not permitted in seismic zones. So, here we have used diagonal bracing. So, typically if your lateral force is from left to right, we can assume that these braces are under compression and these braces are under tension. Now, once we are sure that all these members are structurally safe as per IS 800, because our StatPro is following IS 800 regulations giving us the utilization ratio which is less than 1, we should also check whether the brace satisfies the guidelines provided for ductile detailing in IS 18168. So, in this case we have utilized a square hollow section which is given as tube 100 by 100 by 5. How do you decipher the details of this section? It means that the outer dimension of the section is 100 mm in each direction. 5 mm is the thickness of the section. It is a hollow section, square in shape. So, the width and depth both are 100 millimeters and the thickness is 5 millimeters. The cross sectional area is given as 1836 millimeter square. The second moment of area and radius of gyration is also known to us. These are obtained from the steel table. The elastic section modulus and plastic section modulus are also given over here. Now, as we have discussed in the last class, we need to check the adequacy of brace for its safety in global buckling as well as local buckling. For safety or stability against global buckling, we will consider slenderness ratio. How do you calculate the slenderness ratio? Slenderness ratio is defined as KL upon R, where KL is the effective length of the structural brace and R is the radius of gyration of the structural brace. The effective length of the brace shall be obtained as shown over here, because 5 meter is the bay width, that is the length of the beam or the bay width, 3 meters is the story height. So, the brace which we have provided it diagonally will have an effective length of 5.83 meters. Once we have obtained that, we will divide by the radius of gyration for the brace section, which is 38.4 millimeters obtained from the steel table. We get this ratio as 151.8, and this should have been less than 160 in order to prevent global buckling. So, therefore, this is all right. Later on, probably in the upcoming class, we will also discuss why we should aim for a slenderness ratio which is approaching this higher limit. If it is very small than this, let us say 100 or something, then there is another set of problem which comes into picture because of local buckling. Okay. Let us not digress from this design example problem as of now. Let us now check the adequacy of this brace against local buckling. For checking the adequacy against local buckling, we need to find out the slenderness of various components, whether it is flange or web. For flange, we calculate the flange width to thickness ratio. The width of the flange shall be 100 minus 2 into 5, because 2 times of the thickness must be reduced since it is a square hollow section. So, this very value comes out to be 18, and which is greater than 16.51. From where do we get this magic number of 16.51? From the table 2 of IS 18168, which says that for a closed box section, the outstanding flange width to thickness ratio shall be restricted up to 21.4 epsilon upon a square root of R by. If we calculate this, we get 16.51. We also have very similar value for the closed box section in case of web depth to thickness ratio, and for the web depth to thickness ratio we get again the value as 18, which is exceeding 16.5. Therefore, we must revise this section. So, once we find that this section or this base section is inadequate against local buckling, what does it mean? It means that the thickness of the cross section needs to be increased. If we increase the thickness of the cross section, then in that case what will happen? This denominator will increase, which will reduce this one. So, we want it to be lesser than 16.5. So, that is the way how you tackle this local buckling. But at the same time, what do you expect? With increase in thickness, you will end up increasing Ry, that is the radius of gyration. If you increase the radius of gyration, what will happen? It will also change your slenderness ratio overall. So, let us look into that. In this case, what we do is that we increase the thickness. Now, let us consider the square hollow section 100 by 100 by 6, which means that we have kept the width and depth same as 100 millimeters, but the thickness of the brace section is now 6 millimeters instead of 5 millimeters, which were previously used. The cross sectional area had been found to be 2163 millimeters square. The other properties, second moment of area, radius of gyration, elastic and plastic section moduli are also listed over here using the steel table. Now, we will check the adequacy of this very brace section against global and local buckling. In case of global buckling, we calculate the slenderness ratio KL by R. The effective length remains the same as 5.83 meters. However, the radius of gyration is now 37.9 millimeters. It may not always be true that a section with larger thickness will have increased radius of gyration. As we indicated earlier, it may have reduced radius of gyration depending on the second moment of area and the cross sectional area, because both of them increase and the radius of gyration is calculated as a square root of I upon A. So, in this case we calculate the slenderness ratio to be 153.9, which is less than 160. Therefore, it is alright. At the same time, in order to prevent local buckling, we calculate flange width to thickness ratio as 100 minus 2 times of 6 divided by 6, which is equal to 14.67, which is less than 16.51. The web depth to thickness ratio is also calculated in a similar manner at 14.67, which is less than 16.51. Both of them are satisfying the guidelines presented in table 2 of IS 18168 2023. I have placed a screenshot of the code over here for a better visualization. Here we are using a closed box section, so we should use these expressions. Okay. So, now once we know that this very brace section is adequate against global as well as local buckling, now let us try to design the brace connection. How will you design the brace connection? We all understand that as per capacity design principle, we need to have the bracing connection which is stronger than the brace itself. That is, we want our failure to initiate in the structural brace. We do not want our bracing connection to fail before the failure of the structural brace itself. So, this bracing connection shall be designed for tension, compression as well as flexure. For the tension design, we need to find out what is the expected tension capacity of the brace in both failure modes, that is gross section yielding as well as net section rupture. How will you calculate? For gross section yielding, we will take the value as 1.1 times of Ry times of Fy times of Ag. How did we get this? Ag is the gross cross sectional area times of the yield strength of the material gives us the design strength in gross section yielding. At the same time, we multiply it with Ry, which is the uncertainty factor in yielding, meaning that we want to maximize the capacity of the brace. What is the capacity, maximum possible capacity of the brace, and 1.1 factor is to consider the strain hardening effect. In case of net section rupture, we calculate it as Ru times of Fu times of An. An is your net cross sectional area, which is calculated as gross cross sectional area minus any holes which you already know to find out using your design of tension members, as you would have studied in any course on design of steel structures. Now, Fu is the ultimate strength of the material and Ru is the uncertainty factor in this ultimate strength. Now, the question will arise, why we do not have this 1.1 factor in the second case or the net section rupture case? Because in this case the failure is at the ultimate limit state and there is no strain hardening effect after this stage. Okay. So, here we have calculated these two factors, that is the expected tension capacity of the brace in gross section yielding and net section rupture as 998 kilonewton and 1021.9 kilonewton respectively. The larger of the two shall be considered as the design tensile strength for the bracing connection, because we want to design our bracing connection such that the failure happens in the brace and not the connection. And in this case, while calculating the value of net sectional area, we have assumed that we have connected it using 2 bolts of 20 mm dia, which means that we have used 2 holes which have dia of 22 millimeters. Alright, so we have the design tensile strength of the bracing connection as 1022 kilonewton as shown over here. Now let us try to find out the design compressive strength for the bracing connection. For the design compressive strength of the bracing connection, we usually are interested in the compression capacity of brace, which is generally governed by buckling. So we want to know what is the compression capacity of the structure brace. For finding that out, we need to classify the brace section. So for brace, we have used a square hollow section. For that square hollow section, we will calculate the ratio D by TW, which has been calculated over here as 14.67, which is less than 42 epsilon. In this case, epsilon is equal to a square root of 250 upon 350. So which is giving us 42 epsilon is equal to 35.5. This means that our box section, which have been used as a structure brace, is semi compact in nature. This is as per table 2 of IS 800 2007. Now if you go to table 2 of IS 800 2007, you would realize that box sections can be only classified as either semi compact or slender. They cannot be classified as plastic or compact. Why is it so? Because table 2 deals with slenderness of various components, which means we want to restrict or prevent local buckling of the cross sections. Now tubular sections are prone to local buckling, and therefore we do not assign plastic or compact tags to these box sections. Further, based on table 10 of IS 800 2007, this very box section, that is 100 by 100 by 6, has been classified to have buckling class A about any axis. So based on all of these, we then go to table 9A of IS 800 2007, from where we find out that for the given slenderness ratio of 153.7, we have calculated it earlier as well, and yield strength of 350 megapascal, we get the design compressive strength or FCD as 68 megapascal. Now the area of this brace section is 2163 millimeter square, which is multiplied with 68 megapascal to get the design compressive strength as 147 kilonewton. Now once we have the design compressive strength for the bracing connection ready with us, we will now find out the design flexural strength for the bracing connection. Now as per IS 18168 section 10, this design flexural strength shall be given as 1.1 times the expected flexural strength of brace about critical buckling axis. So 1.1 times of Ry times of Fy into Zp. We have the values of Zp, Fy and Ry known to us, so we have calculated this to be 34.67 kilonewton meter. Okay. Apart from designing the bracing connection for tension, compression and flexure, we should also ensure that the bracing connection should have sufficient rotation capacity such that it withstands rotations imposed by brace buckling. In what manner? It has been shown in this figure. As this very brace has undergone buckling, these connections are subjected to moment, also rotation. So the connection should be able to withstand such rotations which are imposed by brace buckling. Inelastic rotation of bracing connection is permitted. Further, for the gusset plate, we need to detail or design for out of plane bending as well. As you can see that this very brace is imposing out of plane bending on this gusset plate at that end as well. So that should be accommodated. The design shear strength per unit length of weld connecting gusset plate with beam or column flange shall be given as Ry into Fy into Tp upon square root of 3. Alright, this is quite easy to obtain. Fy by root 3 is your design shear strength multiplied with the thickness of the gusset plate and multiplied with the Ry value, that is uncertainty in yield strength of the material. So, by imposing this, we want that after the brace failure, if there is any failure in gusset plate, that should happen much before the connection of this gusset plate with the beam or column flange happens, which means our weld which is connecting gusset plate and beam or column flange should not fail before the failure of this gusset plate. So, that is the idea of what we have introduced through this very expression. Now, in this course we are not going into much detail of an example problem related to this bracing connection, but I hope you should be able to do that or follow whenever you require. Now, let us try to summarize it by giving some regular guidelines on ductile detailing of steel special concentrically braced frames, of which our structural braces are the most ductile element. So, in this case the members are concentrically connected, eccentricity up to beam depth is permitted. Further, the desired failure modes in all these SCBFs is either buckling of structural braces or yielding of braces in tension. Now, there can be different brace configurations as shown over here. These are called diagonal bracing, these are called V bracing, these are called inverted V or chevron bracing, these are X bracing or diagonal bracing, these are multi-story bracing, which are bracing 2 or more stories. So, that is how different types of structural brace configurations are possible. At the same time, K braces are not permitted. We will know more about the reason why K braces are not permitted in the upcoming class. But before that, let us also understand that when in case of steel concentrically braced frames, there are capacity protected elements. What are the capacity protected elements in SCBFs? These are your beams, columns, beam column connections, etc. How do you find the design loads in these capacity protected elements? Now, we do two types of analysis. One analysis is where all the braces are assumed to resist forces corresponding to expected strength in compression or tension. As you can see in this slide, in this case of diagonal bracing, if this brace is under compression, this very brace is in tension. Similarly, at the same time, these braces shall be in compression and these braces shall be in tension. So, we assume that each of them is carrying out its role properly. In the second analysis, we will assume that the tension braces are able to develop expected strength, that is TE, but the compression braces are assumed to develop post buckling strength, that is we assume that there is a global buckling phenomenon already happening in these structural braces. So, in that case the compression braces will be able to contribute only 0.2 times of PE. As per other global codes, this ranges in the range of 20% to 30% of PE. Our code suggests to be 20% of PE. What is PE? PE is equal to Ry times of gamma m0 times of PD. So, once we do these two analyses, then based on these, the larger force determined from these analyses gives us the design forces or moments for the capacity protected elements, and the further detailing are similar to SMRF. Now, there are some more general specifications that we should understand, that the load parts through the braces should be kept consistent. That is, we should not have an offset of the braced bay by more than 10%. That is why you will find in any of the braced frame buildings, whichever bay is braced, that is braced up to throughout the height. Then something related to splicing in columns. These splicing should be developed, these splicing should be able to develop at least 50% of the plastic flexural strength of the smaller connected member, and at least shear strength which is given as sum of MP upon SC. Further, there are some protected zones such as the center 1/4 of the brace length. In the diagonal brace there shall be the center 1/4 shall be termed as protected zone. Then from the connection end, again a zone adjacent which is having length of equal to the brace depth. In our example problem, the brace depth was 100 millimeters. So 100 millimeters from the connection end in the plane of buckling, and any element that connects the braces to beams and columns, which means those gusset plates. There are some other elements as well like knife plate. We are not going into detail of all those, but these are called protected zones, and in these protected zones we do not allow any splicing, we do not allow any holes to be drilled later on in functional period, and so on. In the next class we will illustrate the seismic design of shear links which form an important part of eccentrically braced frame. We will also learn why eccentrically braced frames are superior to concentrically braced frame. Thank you.